In this on-command, on-demand world we live in, information isn't just everywhere. It feels like it is everything.
Absolutely.
From the split second it takes to stream your favorite movie to, sending an email across the globe, we're just so dependent on this huge, complex digital thing behind the scenes.
Mm-hmm. Invisible but essential.
Exactly.
Yeah.
Welcome to the Deep Dive. Today we're kind of unlocking the foundational secrets, the basics of how all that digital magic actually happens.
That's the plan.
Think of this as your shortcut, your guide to the very first building blocks from information storage and management.
Yeah, our mission today is really to dive deep into the core concepts behind data itself, what it is, how we store it, and the frankly sophisticated infrastructure that makes it all work.
Okay.
We want to give you a clear, structured understanding of these fundamentals, provide that context, connect the dots, basically help you navigate the IT landscape, which just keeps getting more complex, right?
Yeah.
So we'll cover everything from, the basic definition of data, how modern data centers work, and even peek inside a hard drive.
All right. So if you're ready to peel back the layers and understand the engine behind our digital lives, let's dive in. Let's start right at the beginning. It seems simple, but it's important. What's the real difference between data and information? People use them interchangeably all the time.
They do, and it's a key distinction. Fundamentally, data is just raw facts, unprocessed material.
Like what? Give me an example.
Think of a handwritten letter or a single digital photograph, maybe a list of sales transactions in a ledger. It's just the stuff itself.
The raw ingredients.
Exactly. It's the facts before you've really done anything with them to figure out what they mean.
Okay, so if data is the ingredients, what's information?
Information is the intelligence, the knowledge you get from that raw data. It's the insight.
Okay.
So businesses, for example, they analyze that raw sales data, those individual transactions to spot trends, like what are people buying, when.
Right.
That analysis, those trends, that's the information. And that helps them plan or maybe change their strategy. It's going from what happened to so what.
That makes sense. And this shift, moving from paper and film to everything being digital, what really drove that? It happened so fast.
Yeah, it did feel fast. There were really three big drivers pushing it forward.
Okay.
First, just the massive increase in data processing power.
Right.
Modern computers suddenly made it possible to convert almost anything, text, sound, pictures, into digital format.
Right, we could digitize everything.
Pretty much. Second, and this is huge, the cost of digital storage just plummeted.
Yeah. Hard drives got cheap.
Exactly. Advances meant really low-cost ways to store tons of data. And of course, if it's cheap to store, you generate and store more of it. It feeds itself.
And the third driver? Speed. Communication.
Precisely. Affordable and much, much faster communication. Think about it. An email takes seconds. A letter used to take, a week? Maybe more?
Yeah, easily.
That speed just makes digital sharing the default. It accelerates everything.
It's also wild how much we create now. Individuals, with our phones and tablets. We're making more data than big companies, aren't we?
That's right. Individuals create the bulk of it. But here's the interesting part.
Right.
While we create it, the value often comes when it's shared. And to be shared effectively, it usually ends up being stored and managed by a relatively small number of organizations.
They were big data centers.
Exactly, in these huge central repositories. And that sheer volume, that scale, that leads us straight into big data.
Big data. Another term you hear constantly. What makes data big? Data. Is it just the size?
Size is a big part of it, yes. Yeah. But it's more than just volume. Big data refers to data sets that are so large or so complex that the normal software tools just can't handle them.
Can't handle them how?
They can't capture the data, store it, manage it, or process it in, a reasonable amount of time. It breaks the old ways of doing things.
So you need new tools, new approaches.
Totally. New techniques, new architectures, often things that can process data in parallel across many machines at once, which naturally makes you ask, okay, how do we actually make sense of all this?
And that sounds like where data science comes in.
Exactly. Data science is kind of the bridge. It's not just one thing. It pulls together statistics, math, data visualization, computer science.
All those fields.
Right. To build algorithms, analyze these massive data sets, and actually pull out tangible business value. Make data-driven decisions, not just guesses.
Got it. Turning the ocean of data into something useful.
That's a good way to put it.
Okay, so all this data, this information, it needs a home. Where does it all live and get managed?
That would be the modern data center. Think of them as the central nervous system for digital information.
Right.
It's where organizations keep and process their data. And the infrastructure is pretty extensive. You've got the obvious stuff like computers, storage systems, network gear.
Servers and racks and blinking lights.
Yeah, all that, but also critical things like power backups, UPS systems, generators, and software, of course, applications, operating systems.
And even the building itself, right? Cooling and things.
Absolutely. Environmental controls are crucial. Air conditioning, humidity control, fire suppression. You need to keep that equipment running reliably and safely.
Okay, so for a data center to actually work, what are the absolute must-have core elements, the essential pieces?
There are 5 key ones that have to work together. First, the application.
Like email or a company's finance system?
Exactly. The program providing the business logic. And how that application works, is it reading data a lot or writing? Is the data access random or sequential, big chunks or small? All that impacts storage design.
Okay, application. What's number 2?
The database management system, or DBMS, this is what provides a structured way to actually store and retrieve all that interrelated data, often in tables.
Got it.
Third, the host or compute system. This is the platform, hardware, firmware, OS that runs the applications and the databases. Could be a big server, your laptop, even your phone in some cases.
Right.
Fourth is the network, the data highway connecting everything together.
Makes sense.
And fifth, finally, the storage itself. The devices that actually hold the data persistently so it's there when you need it later.
Okay, application, DBMS, host, network, storage. They all have to play nice together. Can you give us a quick real-world example?
Sure. Think about ordering something online.
Okay.
You, the customer, use your computer or phone, that's the client. It talks over the network to a server, the host, running the order processing application.
Right.
That application needs to check inventory, record your order, so it interacts with the DBMS on the host.
Which holds the product and customer data.
Exactly. The DBMS then tells the host's operating system, okay, write this order information down. And the OS sends that command, usually over a storage network, to the physical disks in a storage array.
Wow. Okay, yeah, it's definitely a chain reaction.
It really is. Every piece relies on the others.
So when we talk about a good data center, especially the storage part, what are the key characteristics? What makes it reliable and effective?
There are 7 main things we look for, crucial for keeping a business running smoothly. Number 1 is availability.
Meaning the data has to be there when you need it, no downtime.
Precisely. Downtime can cost some businesses millions per hour. It's non-negotiable. Second, security. Policies, tech, procedures to keep unauthorized people out.
Makes sense.
Third, scalability. The system needs to grow easily as the business grows without disruption. Fourth, performance. It has to be fast enough to meet the needs, the service levels.
Okay. Availability, security, scalability, performance. What else?
Fifth, data integrity. You need mechanisms like error correction codes to make sure the data you get back is exactly the data you put in. No corruption.
Super important.
Sixth, capacity. Simply having enough space to store and process everything efficiently, plus the ability to add more easily. And seventh, manageability.
Making it easy to control and monitor everything.
Yeah, ideally through automation. Easy integrated management across all those components.
Okay, that's a comprehensive list.
Yeah.
So what does managing a data center actually involve day-to-day or week-to-week?
It really boils down to 3 key activities. First is monitoring. Constantly gathering data on how everything is doing: security, performance, capacity, availability. Are there any warning signs?
That's keeping an eye on things.
Exactly. Then, reporting. Taking that monitored data and creating periodic reports. How are resources being used? Is performance meeting goals? This helps justify costs and plan for the future.
Okay.
And third is provisioning. This is the act of actually allocating resources, setting up new servers, adding storage, configuring software to meet those ongoing requirements for capacity, performance, security, and availability.
Monitoring, reporting, provisioning. Got it.
Yeah.
Now let's zoom right in on the storage itself, the devices. What are we talking about here?
These are just the physical things designed to hold data long-term. We see them everywhere, right? Media cards and phones, DVDs, CDs.
USB sticks.
Yep. And of course, the hard disk drives in computers and servers. They use different technologies, magnetic like disks and tapes, optical like CDs and DVDs, or solid state like flash memory.
Tapes and optical still have uses, but for applications needing high performance, disk drives have really been the standard for a long time. Why is that?
It really comes down to access speed and randomness. Disks are very good at quickly finding and reading or writing data anywhere on the disk surface, random access.
Not like a tape where you have to wind through.
Exactly.
Yeah.
That random access is crucial for online systems where many users might need different bits of data almost simultaneously. Plus, they offer huge capacities, especially when you group them in arrays.
Okay, let's unpack that.
Mhm.
Hard disk drive, the HDD, it's kind of amazing it works at all
Oh.
with spinning parts. What's actually inside?
It is pretty amazing tech. Think of it like a super precise miniature record player. You've got the platter, that's the actual disk, round and coated with magnetic material where the data bits are stored. Most drives have several platters stacked up. These platters are mounted on a spindle, which is spun by a motor at really high constant speeds, anywhere from, say, 5,400 RPM up to 15,000 RPM in high-performance drives.
Wow, that's fast. And how does it read and write?
That's the job of the read-write head. It's a tiny little component that floats incredibly close to the platter surface.
Floats. It doesn't touch.
No, and that's critical. During normal operation, it never touches. There's a microscopic cushion of air generated by the spinning platter called the head flying height. It's unbelievably small.
Okay.
The head changes the magnetic polarization on the platter to write data and senses it to read data. An actuator arm assembly moves the head back and forth across the platter very precisely, and a controller board manages all the electronics and communication.
So if that head does hit the platter, that's the dreaded head crash.
That's exactly it, and it's usually bad news. The impact scratches the magnetic coating, destroys data in that area, and often damages the head itself. Game over for that drive, usually.
Yikes. Okay, so given all these moving parts and tiny tolerances, how do we measure disk drive performance? What matters?
There are three main factors we look at. First is seek time, sometimes called access time. That's how long it takes the actuator arm to move the read-write head over the correct track on the platter.
How long does that take?
We're talking milliseconds, typically between 3 and 15 milliseconds for modern drives. There's even a technique called short stroking to minimize this, where you only use the faster outer tracks, but you sacrifice capacity.
Interesting. Okay, seek time. What's next?
Second is rotational latency. Once the head is over the right track, you have to wait for the platter to spin around so the specific data you want is directly underneath the head.
Depends on the RPM.
Exactly.
Yeah,
Faster RPM means lower latency. For a 15,000 RPM drive, it's around 2 milliseconds on average.
Okay, seek time, rotational latency, and the third.
Data transfer rate. This is basically how fast data can move on or off the disk once the head is in position. There's an internal rate platter to the drive's own buffer memory, and an external rate, which is how fast data moves through the interface, like SATA or SAS, to the host. That external rate is usually the advertised speed, but the sustained rate you actually get is often lower due to those seek and latency times.
Right, the real-world speed. Now, you mentioned the controller earlier. How busy that controller is affect performance?
It's a huge factor. Think of the disk's I/O controller like a traffic intersection.
Okay.
If the intersection isn't busy, requests flow through quickly. But as more and more I/O requests arrive, the controller gets busier. As its utilization climbs towards 100%, things start to back up badly.
Like a traffic jam.
Exactly. Response time, how long it takes for an I/O request to complete, just skyrockets. It becomes a bottleneck.
So you don't want to run your disks at 100% utilization.
Definitely not if you care about performance. For applications that need fast responses, it's common practice to keep disk utilization below 70%. That leaves enough headroom to handle peaks and keep response times acceptable.
Wow, okay. That has big implications for planning then. How do you actually figure out how many disks you need? It's not just about capacity, is it?
Not at all. This is where it gets interesting and sometimes counterintuitive. You have to calculate the number of disks needed for capacity and the number needed for performance, and then take the higher number.
Okay, walk me through an example.
All right. Let's say an application needs 1.46 terabytes of storage space. That's the capacity need.
Okay.
And let's say at its peak, it generates 9,000 I/O operations per second IOPS. That's the performance need.
Right.
Now, suppose you're using disks that are 146 gigabytes each and rated for a maximum of 180 IOPS
Okay.
for capacity. 1.46 TB is 1,460 gigabytes. So 1,460 gigabytes divided by 146 gigabyte per disk means you need 10 disks just for space.
Simple enough.
But now, performance. We want to keep utilization below 70%. So each disk can reliably handle 180 IOPS times 0.7, which is 126 IOPS.
Okay, 126 IOPS per disk reliably.
Right. So to handle 9,000 IOPS total, you need 9,000 divided by 126 IOPS per disk, which comes out to about 71.4. You can't have part of a disk, so you round up. You need 72 disks for performance.
Wow. So 10 disks for capacity, but 72 disks for performance.
Exactly. And since you need to satisfy both requirements, you have to go with the higher number. You need 72 disks.
That's fascinating. Performance is dictating the disk count, not capacity.
Very often, yes.
Mhm.
Especially for transaction-heavy applications, you end up buying way more raw capacity than you strictly need just to get the necessary IOPS.
That explains a lot. But HDDs aren't the only game in town anymore, right? What about flash drives, SSDs?
Right. Solid-state drives, or SSDs, have really changed the landscape. They use semiconductor memory flash chips instead of spinning platters and moving heads.
No moving parts.
No moving parts at all, which means no seek time, no rotational latency.
Ah, so they're much faster.
Dramatically faster, especially for random access. Response times are incredibly low, often under a millisecond. Plus, they use less power, run cooler, and are more resistant to shock.
What kind of applications are they best for?
They excel where you have lots of small random reads, think databases, currency exchange platforms, real-time analytics, anything needing super fast response.
And what about the overall cost? They used to be really expensive.
The cost per gigabyte is still higher than HDDs, but the picture is changing when you look at total cost of ownership, or TCO.
How so?
Because they deliver so much more performance per drive, you need far fewer SSDs to achieve the same IOPS target as HDDs, maybe 20 or 30 times fewer.
Right, like in our example, instead of 72 HDDs.
You might only need 3 or 4 SSDs to get 9,000 IOPS, so you save massively on the number of drives, the enclosures, the power, the cooling, the floor space. The overall TCO can actually be much better with SSDs for performance-critical workloads.
Okay, that's a really important perspective. So we understand the drives. Now, how do the hosts, the computers and servers, actually talk to these storage devices?
That's all about connectivity. It's the physical links and the languages or protocols they use to communicate. We're focusing here on how a host connects to storage.
Let's start with the physical parts. What connects them?
There are 3 main physical components involved. First, you have the host interface device. This is the card or circuitry in the host that provides the connection point.
Like a network card.
Similar, yes. For storage, we often talk about host bus adapters, or HBAs. For network communication, it's network interface cards, or NICs. HBAs are specialized to handle storage I/O, taking that load off the main CPU.
Okay, HBA or NIC. What else?
Second, the port. That's just the physical socket or connector on the HBA or on the storage device itself where you plug in the cable.
Right.
And third, the cable. The physical wire or fiber optic strand that carries the signals between the ports. Copper for shorter distances, fiber for longer and often faster connections.
HBA, port, cable.
I got it.
And the protocols, the languages they speak over those cables.
There are several popular ones. For connecting drives inside a computer, you've had IDIATA. More common now is its successor, Serial ATA or SATA. It's cheap, pretty fast. SATA 3 goes up to 6 gigabits per second.
Okay, SATA is common. What else?
For higher-end systems, especially servers, you have SCSI, Small Computer System Interface, and its modern serial version, Serial Attached SCSI or SAS. SAS also hits 6 gigabytes or more now and offers more features than SATA, often used in enterprise storage.
SATA and SAS. What about connecting to storage outside the server over a network?
Right. For dedicated storage networks, Fibre Channel FC has been a mainstay for years. It's high-speed, reliable, designed specifically for storage traffic. Speeds now go up to 16 gribs or even higher.
Fiber channel, okay.
And increasingly, you see storage accessed over standard inter-protocol IP networks, the same networks used for regular computer traffic. Technologies like ISCSI, which runs SCSI commands over IP, or NAS protocols fall into this category.
So lots of options depending on the need. Now, if the storage is just plugged directly into the server, what's that called?
That's direct attached storage, or DAS. Just like it sounds, directly attached. Yeah. Simple, but doesn't scale easily and isn't easily shared between servers.
Right. The network-based options fiber channel, IP storage, allow for more sharing and scalability, I imagine.
Exactly. Those network-based approaches, whether they provide block, file, or object storage, are really the foundation of modern data centers. But those are deeper topics for another time.
Okay. Finally, let's touch on 2 big concepts we hear all the time. Virtualization and cloud. How do they fit into this storage picture?
They're hugely important. Let's start with virtualization. At its core, it's a technique for abstracting physical resources, making physical things appear as logical things.
Abstracting. What does that mean in practice?
It means hiding the underlying physical complexity. Think about partitioning a single physical hard drive into multiple logical drives, like a C drive and a D drive. That's a simple form of storage virtualization that's been around forever.
Okay, I get that. What's the big advantage?
The main benefits are pooling and flexibility. You can pool multiple physical resources together, servers, storage devices, networks, and present them as a single, unified resource pool.
So many small disks look like one giant disk.
Sort of, yes. Or many physical servers act like one big compute resource.
Yeah.
It also allows for much more flexible allocation and centralized management of those resources, makes things way more efficient.
Can you give us a quick rundown of the main types of virtualization relevant here?
Sure. There's application virtualization. This kind of packages an application with just the bits of the OS it needs so you can run it anywhere without installing it traditionally. Helps avoid conflicts between apps.
Okay.
Then there's compute virtualization. This is probably the most common type. It abstracts the physical server hardware, allowing you to run multiple operating systems, each in its own isolated virtual machine, or VM, on a single physical server.
Right, VMs, that's everywhere now.
It really is. It's managed by a software layer called a hypervisor. And third, there's desktop virtualization, or VDI.
What's that?
This abstracts the user's desktop, the OS, apps, data from their physical device. The actual desktop runs on a VM in the data center, and the user accesses it remotely from a laptop, thin client, even a tablet.
Ah, so your desktop follows you around and the data stays secure in the data center.
Exactly. Big benefits for security, management, and backup.
Okay, that's virtualization. How does the cloud relate to all this?
Cloud computing is essentially a model for delivering IT resources, compute, storage, networking, applications as a service over a network, usually the internet.
So it's like renting IT resources instead of buying and managing them yourself.
That's a good way to think about it. And crucially, the infrastructure behind the cloud services offered by providers like AWS, Azure, or Google Cloud, it's heavily built on virtualization.
Ah, so virtualization enables the cloud.
To a large extent, yes. Cloud leverages that resource pooling, the rapid provisioning, the scalability that virtualization provides, and packages it up as an on-demand service. It's a different way of consuming and managing IT, driven by cost savings and the need for agility.
Got it. Virtualization is the tech, cloud is the delivery model.
In simple terms, yeah.
And there you have it. Wow. Our deep dive into the Introduction to Information Storage module. We've covered a ton of ground.
We really have.
From defining data versus information, right through the guts of a hard drive, the key elements of a data center, and touching on virtualization and cloud.
Yeah, we looked at why information is so vital now, those 5 core data center elements, how hosts and storage talk, the performance calculations.
The performance calculation was eye-opening. 72 disks.
It often surprises people, and we saw how virtualization and cloud are really changing the game for provisioning and management.
It's incredible how fast this field moves, but also how these fundamental concepts, how a disk works, what availability means, are still the bedrock of everything digital.
Absolutely. You really need this foundational knowledge to understand anything more advanced in IT today. It lets you appreciate the complexities and make better decisions.
So for you listening, maybe think about this. How might knowing that performance, not just space, often dictates storage needs, or understanding the delicate mechanics inside a drive? How might that change how you think about your own data or your company's IT choices?
It's worth pondering. We hope this dive has given you a clearer map and some solid insights into the world of information storage.
Until next time, keep exploring, keep learning, and keep diving deep.